I think we've done an inverted cone, or at least a cone problem. I can't remember if it was in the same position that it is here. But here we have a cone that water is flowing into, and the water is flowing in at a rate of 2 cubic meters per minute. And that cubic meters per minute should be your first clue that what you know is that the rate of change of the volume is equal to 2. Okay, and if you want to put the units of measure here, I usually don't. But anyway, because I can just read them in the problem. But dV dt is equal to 2. And it's asking for how fast is the water level rising when the water is 5 feet or 5 meters deep. So that's what we want. So I labeled a two-dimensional figure over here to the right. I labeled that with the h of the water, the height of the water, and also the radius of the water, where we know the dimensions of the actual cone are 16 feet high. Sorry, I think I keep saying feet, but it's meters. 16 meters high and a radius of 4 meters. So the radius is always going to be 1/4 of the height. Okay, so that's key information there, but we'll get to that. Okay, but what we want to know is how fast is the water level rising. Okay, so we want to know what dH dt is at the precise moment when the water is 5 meters deep. Okay, so because I've already labeled my diagram, I can write that as dH dt at the moment that h is 5. And then we know that we're given here the volume of a cone, which is 1/3 pi r squared h. Okay, well this is the tricky part. Okay, notice that what we want has an h in it, and what we know has a v in it. Okay, well there's no r in either of those statements there, and so since there's no r, we want to get rid of our r, and that's the little extra work that you have to do. Okay, so we're going to do a little extra work in the lower right hand corner here. And this is the part that it relates back to geometry. So when you learned similar triangles in geometry, part of the reason why you learn that is because now you have to use it. Alright, well, similar triangle said, like I said, the radius, the ratio of the radius to the height of this cone is 4 meters to 16 meters. Okay, so 1/4 is the ratio of the radius of the cone to the height of the cone. Well, it still applies when the water level is rising. The radius of the water is equal to 1/4 of the height of the water. Okay, so if we wanted to solve for r in terms of h, we'll take this equation, r over h equals 1/4, and if we multiply both sides of that equation by h, what we end up doing is something that's really convenient, because we don't want to have an r and an h in our relate equation, because that's confusing when we try to differentiate, because we don't have anything to substitute for the r, or we don't even know what the dr dt is. So that's why we're going to get rid of our r, because all we know only something about the volume rate, and then we want the rate at which the height is changing. So we're going to get rid of the r. Alright, so the r is equal to h over 4, and this is our key relationship between our r and our h, and so we're just going to use that in our equation. So we're going to substitute that in. We have, let's write the 1/3 pi as pi over 3, and the r, again, looking over there, is our h over 4. So r is h over 4, but don't forget we have to square that, and then that gets multiplied by the h. So we're really going to be able to conveniently express our volume in terms of just h, and then we can differentiate. So we have pi over 3 times h squared over 16, multiply that by h, and let's clean it up even further. Let's write this as pi squared, sorry, not pi squared, pi over 48 multiplied by h cubed. Okay, so that's a really convenient expression for the volume of our cone. Okay, so let's do our work way up here. Okay, so I'll rewrite that. Volume equals pi over 48 h cubed. Now, this is probably obvious too, but I thought I'd state it anyway. This is not always going to be the volume of a cone. It's only the volume of a cone that has a radius of 4 and a height of 16. In other words, the radius of this particular cone is always going to be 1/4 of the height. So any other cones may have a different ratio, so then therefore you'll have a different volume equation. Okay? But now at this point, hopefully by now this is second nature to you. Want, know, and relate, and then you differentiate. And so on the left side we're going to get our dV dt equaling on the right side 3 pi over 48, so 3 times that constant out there, multiplied by h squared, but don't forget about the multiplied that by dh dt. Okay, so we do want our dh dt at the precise moment when h is equal to 5. And so we can see, if we look at our equation, do we have to work for anything else? We know our dV dt. We know we want our dH dt at the precise moment h is 5, so we really have no other values to plug in. So we have no other values to work for, so let's just plug in dV dt, and that is 2 equals our 3. I really don't like writing it red like that. Let's do blue. Okay, so our dV dt is 2. We can say, so 2 equals 3. Oh, let's clean this up a little bit. 3 goes into 48 16 times, so we can write that as pi over 16 multiplied by h squared. The h, again, at the point that we want our dH dt is 5, so 5 squared times dH dt. Okay, and then we have 25 pi over 16. By the way, I had learned that this is it's a popular, I shouldn't say that. We'll just forget what I just said. 2 equals 25 pi over 16. Multiply that by dH dt. And so then we're going to multiply top and bottom of each fraction by 16 over 25 pi. 16 over 25 pi. And on the left-hand side, we get our final answer of 32 over 25 pi, and that is equal to our dH dt at the moment when h is equal to 5. So that's my answer, but let me make sure I answered the question correctly. How fast is the water level rising when the water is 5 meters deep? Okay. Well, then we would say, so our answer, let's put it in this box right here, we would say, therefore, where's the answer? 32 over 25 pi, and this is a height, so it's just meters per minute. 32 over 25 pi meters per minute. That's a really, really good question to know how to do. Involves a little geometry, but it also has all kinds of other good stuff in it. Okay, so I'm just looking at the surveying the problem here. That's a really good problem to know how to do. If you know how to do that problem, you can do many of the related rates problems that you'll see either on a multiple choice test that you'll see here in a couple days, or the final exam. It's a great, great test question. So hopefully you're absorbing that, and if you have any questions, let me know.